Okay, so working with Sean, I asked Sean the yield strength, or the strength of that 5-inch thick 4040 steel for the safety beams on the hydraulic press, and he was right. It was about 100,000 psi, and I still couldn't help but to wonder exactly what would it look like if we did hit it with 5 million pounds of force, or 5 million pounds of weight. And because we have 2 bars in this particular simulation, I only have the 1 bar, so I'm going to do a stress load of 2.5 million pounds on it, because we should be able to disperse the weight between the two. And I found some interesting things that that we definitely need to be aware of. If this thing were to come down, it could launch this 300-pound steel safety dowel at 49.6 miles per hour up to 163 feet. So keep that in mind, because you don't want to be that guy right there when a 300-pound, 50-mile-an-hour object's flying right at you. So we're going to cover over a couple things that I discovered about this. Here I've kind of got the shop modeled out, and we're going to jump over to generative design to run simulation. And here in the simulation, let me switch over to Sim 2. Now this simulation cost me $300. So here's my receipt on it. But I don't want to sit around this. I paid for this on my own pocket, because I kind of want to know, because I'm kind of scared of that big press, and I was curious this Thanksgiving morning to see what I'm in for if I'm going to be sitting across there. What can happen? So here's kind of a layout of the VF10, VF4, the lathe, the Fadal, and not shown here is a reflective danger zone, and this reflective danger zone. So that color there. This zone right here is, some other considerations where even if it flies out, and it doesn't hit anything, it's coming full force at you. But if it flies out and hits the press, it's going to lose a little bit of, velocity, but not a lot. And it's going to have a lot different vector with just, slightly reduced magnitude. But if it hits that press, if we're to fly out and hit that press, as the simulation at the start of the video showed, there's a lot of places that thing can go, and it can still have a travel range of 130 to 163 feet. I'll show you the mathematics and physics behind it. So let's go ahead and dive on in here. So to isolate the stress load on just the safety beam by itself, we're going to do a structural buckling simulation test right here. We're going to put 2.5 million pounds on this, and just to save you a little bit of time, we're under the safety rating by 500,000 pounds. But I'll show you what it looks like. Now keep in mind, this is what this dowel will look like just sitting 2.5 million pounds on top of it. This does not take in consideration dynamic force of the press slamming down on it. Now we have a radically different problem. This is just a static structural buckling simulation here. So if I come over here to the results, not too bad. So you think not too bad, right? Here's the thing: if the surface of the coplanar surfaces from this top of the safety dowel, as I like to think of it, 5-inch 4040 safety dowel, if it's not perpendicular to the top of the press, if there's any angularity at all, like if Sean bandsaw cut it, but there was just a slight degree of angle, like 1 or 2 degrees of angle, can radically shift the projection or the trajectory of this thing if something were to slam down on it. And the armatures that hold this thing on, that 5 million pounds would laugh at. It would laugh at it. It's going to tear that all apart, and it's going to come flying out. So anyhow, I did not run a full rigid simulation like I'd like to on the armatures, because I didn't sit there and design them exactly how Sean has built them. So I didn't want to run any inconsistent test. And then plus, every time I run this thing, it's $300. I paid $300 for just 100 cloud credits, and it was like 25 credits just to run this one simulation. So I'm being picky about it. But I want to show here, that's 2.5 million pounds, and doesn't look scary, but there's a lot of danger behind that. Let me and we can do a simulation on 5 million pounds. for one bar to see what it looks like out of curiosity. But I'm going with the actual load that each dowel is going to take. So if there's 2 of them, they're going to split 5 million pounds. They're going to take 2.5 million pounds each. Here's the breakdown analysis to keep things short. If we have a 5-inch round solid 40-40 steel bar that's 3 feet long, and it's at vertical like a column used as a safety in case a 5 million pound press hydraulics fail, what would would it bend this column? And as everyone predicted, the compressive stress exceeds the yield strength of material, and the column would fail by material yielding under the given load. The critical buckling load is 2.09 million pounds, which is far below the applied 5 million pound load. Therefore, the column would fail by buckling. Well, even if we evenly distribute between two different safety bars, we're still 500,000 pounds under safety rating to keep it from bending. That bending could turn into a real. That's what turns into a real nasty problem, and that's just force literally applied to the top, non-dynamic force, nothing dropping on it. The dropping factor, like if that thing is all the way up and it slams all the way down, that's where we look at the real danger, and why we really need to consider the excess safety factor. With the same material and situation under a 2.5 million pound load, would the column still fail? So here we go back to testing a single one. I first asked AI and got all this information. Here's all the physics calculations to determine column strength, compressive stress, elasticity of the 40-40 steel to see if it's going to buckle under such a load, and and it's needless to say, it's really dangerous. We really need to beef it up a little bit more. And I got the solution for it. So I asked it I asked artificial intelligence, how far does it predict in a worst case scenario this thing could launch that 300 pound 40-40 steel beam at somebody, and it did all the kinetic calculations, it did all that fun stuff for us, and it concluded that if the column buckles violently, its stored energy released entirely, it could launch at a velocity of 22.1 meters per second, or about 50 miles per hour, and it could travel up to 163 feet. This demonstrates why failures are extremely dangerous and must be mitigated with proper safety measures. So I went on to ask it further questions, angularity questions, and here's the summation of everything. So we're not diving through tons of the calculations and particulars. If the column had any sort of deviation in its flatness and it buckled, could it fly out and kill somebody? Again, going back to when Sean cut it, if it wasn't perfectly flat like you would do on a like you would have on a lathe, like if you cut it on a lathe, it would be perfectly flat. If it's not perfectly flat, I'm not sure how it got cut. I'm just emphasizing here, if there is any deviation to the flatness, this presents a huge problem. AI does confirm that yes, if the columns buckle and fails under load, it could potentially fly out and pose a serious risk, to nearby individuals. Please forgive me, I'm sick. I did a COVID test and a flu test, and I passed both of them. I don't have COVID or flu, but me and my entire family are sick here on Thanksgiving Day. Anyhow, how far could the stored energy launch the steel beam? As we know, we covered over that it can launch it at 50 miles per hour and up to 163 feet. That puts a lot of people into the kill zone. So this 3D model here that I put together, I don't remember all of Mike's design, like how big the buildings were. I remember some parameters, but essentially on a 163 foot kill zone, from here on out, if you're in the red zone, you're dead. Now, do know that the significance of the coplanar faces on those safety beams, if they do have angle and they were in this thing, let's say this thing were to really really slam down. Let's see if I can edit that joint. If this thing's just like bam, I mean, when it's coming up and down, if it were just to slam down, that's where we have real problems. The test that I did, where I'm showing you the bar stock at a slight bend, that's as if we just drop this press down and then put a hydraulic load on it, and even that is dangerous. But where it's really dangerous is if this thing, from what I got told, this thing comes up and it just slams down and presses everything. If for any reason this came to slam down on top of that beam, the dynamic force impact I haven't done a simulation on because it was $300 for 100 credits. and that thing is going to be like a 30 credit round. It's going to be really expensive for me to do it. But needless to say, I'm not really wanting to be around this thing when it's going off. And some of the more comprehensive data coming back from the questions that I had, as well as the simulation I ran, would 4 of those 5-inch thick columns be capable of handling the stress load? And the answer is yes. 4 of them would be able to handle up to 8.36 million pounds. We would be in excess of 3 million pounds of safety rating. Right now, with the 2 beams, we are actually 1 million pounds under safety rating. I mean, if that thing comes down, we have 1 million pounds of stored energy that could do something unpredictable. It's not comfortable to me. And I was hoping that, you know, when I plugged all this data in, that I would have concluded that the thing is going to be safe. But as it is right now, the 2 bars is not adequate. It's 1 million pounds of safety, under safety rating, compared to the math here. And I suspect, after looking at this thing and thinking about it, I suspect because the other bars, the previous bars that we replaced were 4 inches in diameter, they were probably a lot less strong. I think this thing probably could have killed somebody in its time. I mean, I wouldn't put it past this machine if it had a fatality in its history. It's definitely dangerous. Everything about it is really dangerous. So again, I didn't trust, I didn't necessarily trust AI in the sense that it's not going to show me a simulation. It's not going to map everything out. It gave me all the beautiful quantifications on different strengths, and it did the physics beautifully to answer my questions on buckling load and predictable analysis. But I had to actually run a simulation on it to kind of gain the ideal of the footprint of the kill zone that we're in if this thing were to fail. And that's why I ran the simulation here, and that's why I went ahead and paid for it, because I'll be sitting in that office as well. And essentially, if that thing does come flying off, if you're in the office here, if we're working on the VF10, and if there is any angularity in the safety down, as I call it, the 5-inch 40/40 safety column, if there's any angularity in that, and this thing slams down with dynamic force, it could potentially make its way to the VF4. Yeah, there's some magnitude maxims that can allow it to launch in this distance. So everything here is pretty much in a danger zone. Now, when you look at the just common sense, without doing any kind of math or anything, when you look at the press to the position of the when you look at the 5 million pound press compared to this other press, everyone that's working on like the Fadal, if you're over here in the Fadal, you're not too bad in the danger zone. The water jet machine, the Thermwoods, all the Thermwoods over here, the Thermwood right here. The old one, if you're working on the old one, maybe a little bit, but the newer one's got like, you got a wall of some metal there to maybe protect you. So just something to keep an eye out for, something to visualize, and kind of why I put this together and ran this simulation. And anyhow, I just hope this helps out, give some feedback. I kind of want to simulate what it would look like if I did a dynamic force impact. What would happen? This thing will probably crinkle like a C. It would probably look like the shape of a C under a dynamic force impact versus just a structural buckling load test. Because what we're looking at right here, that's kid work. That's like best case scenario at 5 million pounds, just sitting atop of it for structural buckling. Dynamic force load is going to be a whole nother creature, and that's why I don't want to be anywhere around this machine until we're in excess of safety ratings, because right now I have full proof of why I don't want to be around that machine. So anyhow, I hope this helps out. Thank you for watching.